So we've been talking about the maximum fixed point or MFP solution of a data flow analysis. And let's try to understand how does the MFP solution compare to the best possible solution that we could have had, right? So recall that the maximum fixed point MFP represents the most precise maximum solution that satisfies the data flow equations. What are the data flow equations? Data flow equations are formed by the transfer functions and the meet operator. And so assuming that the meet operator is as it has been given and the transfer functions are also as they have been given, so we're not allowed to change either the meet operator or the set of values v or the transfer function, is this the best possible answer we could have got with the most powerful analysis that we could have had for our program? And if it is not, then how does it compare with that? And that's the question we're going to try and answer in this particular lecture module. So we want to ask, is that the best possible solution? Once again, I want to emphasize that we are not allowed to change the transfer functions. We are not allowed to change the set of values. We are not allowed to change the meet operator. But even with these constraints, can we do better than what MFP gives us? Recall that MFP is the maximum solution that satisfies the data flow equations. Okay, so let's call the best possible solution the ideal solution, and let's see what ideal could potentially look like. So to be able to define an ideal solution in this setting, we are going to define the transfer function of a control flow graph path. All right, so we already know what is the transfer function of a statement. We also know what is the transfer function of a basic block that's formed by composing the transfer functions of the individual statements in that basic block. But now we want to talk about the transfer function of a full path. So given the transfer functions of each statement or CFG node, we can construct the transfer function of a CFG path. So let's say this is my CFG, and let's say this purple line here is a CFG path. Notice that the CFG path is allowed to have cycles. So for example, I could go twice or 10 number of times around this loop and then come out. And that would also constitute a valid CFG path. And so we can talk about the transfer function of this whole path. So even if I have gone around the loop 10 times, what is the transfer function of this whole path? That is basically answering the question that if I have a value x in the beginning of this path, then what is the value fx that is coming out at the end of this path? And so to define the transfer function of a path, we're going to use this definition, which is the intuitive obvious definition, that the transfer function of an empty path, and a path which has no nodes whatsoever, is just the identity function. And recall that the identity function is supposed to be in our family of transfer functions. So f of epsilon x is just x. And then transfer function of any other path which is formed by nodes or statements s1, s2, dot, 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 sn. And notice that this path can have cycles. So for example, the same statement may repeat multiple times in this particular path. So it could be, for example, s1, s2, s3, s2, s3, dot, 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 sn, and something like that. And so this path, what is the transfer function of this path? It's given by fp of x is first apply fs1 of x, so that's the first statement that got executed, then apply fs2, then apply fs3, and so on, and finally apply fsn minus 1 and fsn. In other words, the transfer function of a path fp is basically the composition of individual functions fs1 composed with fs2 composed with fsn. So this is the short way of writing composition. This is a slightly longer verbose notation of writing function composition, but both of these notations are basically saying that the transfer function of a path is formed by composition of the individual transfer functions that constitute that path. Alright, so now with that we are going to define the ideal solution, and the ideal solution in this setting is that what is the best possible answer we could have expected? The best possible answer is for a program point, take all the program paths that can reach that program point from the beginning of the program, assuming it's a forward DFA. If it was a backward DFA, then I would talk about from the exit to that program point, what are all the possible paths. But without loss of generality, let's talk about forward DFA. In a forward DFA, we are interested in all possible paths that may reach a program point starting from program entry. We are interested in those paths that are possible to execute. So for example, if there is some path which is never going to execute. We are not going to take that path. All right. So we are interested in all such paths, and there can be infinitely many such paths, especially because there are cycles. But let's say we are able to basically compute the transfer function of all such paths, and then we meet over all such paths the values, and that is the value that we get. So we take fp of n. For at node n, we want to compute the value vn, and for a forward data flow analysis, maybe we want to compute in of a basic log. For a backward data flow analysis, maybe we want to compute the out of a basic log. Whatever it is, I'm representing it using this identifier called v. Then that is basically all the if I take the mean over all the possible values that may reach that program point, then that would be the right answer. That would be the best possible answer, because after all, whatever value I decide for that particular program point, it has to be less than equal to all the other values that can reach there. And so what is the value that is less than equal to all the other values that can reach there? It's the meet of all those values. And so that's what this expression is showing. It's a meet over fpn, where we meet over all, where p is basically an execution path that may reach n from the beginning, assuming it's a forward DFA. Notice that the word execution here is important. So we are only interested in those paths that can potentially be executed. If there are some paths that may not be executed, we are not interested in capturing them. This is the best possible answer that I can expect with a given transfer function for every node and for a given meet operator. All right. Now, so I'm going to call this the ideal solution. So let's try to understand the ideal solution with an example. So let's use the constant propagation DFA example that we've been using all through the course. And let's say this is my program, which says y equals SQR of x, and then it checks y is greater than equal to 0 or not. If this evaluates to true, then I set x to 3. If it evaluates to false, then I set x to 5. Now notice that the function SQR is actually intended to represent the square of a value. So it's going to take the square of x, right? So y is equal to x squared. Now, initially, we assume that the value is the empty set, which means we don't have any constant relationships that are known. And then we want to know what is the best possible solution that is possible in this case. Now, the reason this example is interesting is because if y is x squared, then we know that y will always be greater than equal to 0, and that means that the false path is not executable. In other words, no execution of this program will ever take the false branch. In which case, the only path that is possible is the true path, and so our ideal solution should take that into account. Recall that the ideal solution basically meets over all executable paths or all execution paths, and false branch is not an execution path. All right, so this is our solution. It starts with empty set. After y equals square 0, it still remains the empty set, the value for the constant propagation. It remains empty set here, remains empty set here, but after x equals 3, we know that x is now 3 at this particular program point. So we have this particular value which maps x to 3. Similarly, on the false branch, we have 5, and then we have x equals 5 just after x equals 5, because this statement x equals 5 is generating a mapping x comma 5. And then at this particular point, right, the beginning of this fourth basic block, we meet the two values, which is x equals 3 and x equals 5, and there's nothing common here. The meet operator is intersection, and so we again get the empty set. Now let's look at the ideal solution. Recall that the ideal solution is basically look at all the paths that reach this point, all the execution paths, and then meet the value. So what are all the execution paths? Well, in this particular example, there's only one execution path. And on that execution path, the value that will come here is 3. And so the ideal solution should have been x equals 3. So it's clear that the maximum fixed point solution is not equal to the ideal solution in this example. In fact, it is less than equal to the ideal solution, where less than equal to is defined on the semi-lattice. So why is this happening? Well, that's happening because we don't have any way of figuring out what are all the paths that have been taken in the program, what are all the execution paths, and that seems like a difficult problem. In fact, instead of SQR, if I had just some random function called foo, maybe that function foo had some very complicated and convoluted logic, and somehow it was true that it would only return positive numbers, but to be able to do that analysis is difficult. And in fact, it can be shown that in the Turing model of computation, identifying whether y is greater than equal to 0 or not for all possible values of x is undecidable in general. okay, for an arbitrary function foo. And so identifying, and from that we can also figure out that identifying the ideal solution at any program point is undecidable. So so that's why, it seems like it's a very difficult problem to solve, that is find the ideal solution even when the transfer functions and the meet operators are fixed, even when the transfer functions are monotonic, even when the semi-lattice is finite height. Finding the ideal solution is still undecidable because we don't know which parts may get executed in the program at runtime and which parts may never execute at runtime. Okay, so precisely identifying all the program paths that may reach a program point is undecidable in general. Identifying all the program paths that may reach through execution, right? Or maybe I should be clearer here. May reach through execution. Okay. But ideal is still a good, nice theoretical concept, because at least we should be able to look at a program, and if we can reason about some things manually, we should be able to say, okay, this is the ideal solution and this is the MFP solution and this is the gap between the two solutions. All right. So there is another approximation to ideal. So maybe ideal is very bad. It's very difficult to compute because we have to figure out what are the executable paths, and we just showed that this is an undecidable problem, that what are the executable paths and what are paths that are not executable. But how about we just conservatively assume that all paths are executable, all paths that reach that program point are executable, in which case our ideal solution will be called a meet over path solution. So it's the same concept as ideal, which means I'm going to meet over all the paths that reach that program point, but now I'm not going to do that only for the paths that are executable, but for all possible paths that reach that program point. And so I'm going to define a meet over paths, or MOP solution, such that at node n the value Vn is meet over all paths that may reach n. All right, all paths P that may reach n, and we meet and we basically apply the transfer function for that particular path. Once again, there's an infinite number of such paths. In fact, the set of all paths is of course is a superset of all the execution paths, and so this expression should be less than equal to the ideal solution. We're going to discuss that in a moment, but this seems like an easier quantity to compute, because now we don't have to worry about what paths are executable and what paths are not executable. In our previous example, for example, we don't have to reason about whether square will or whether foo will always return a positive number or not. We really don't care. In the meet over path, we're just going to conservatively assume that foo may return both positive and negative numbers, and so we have to meet over both the paths. So unlike ideal, MOP includes paths that may never be executed, and so it's a conservative solution. It's a more conservative solution than ideal. But does it make our problem easier? Well, it does, because MOP is no longer an undecidable problem, identifying the MOP solution. And so let's understand what is the MOP solution for this particular example that we saw in our previous slide. Here, once again, on one path we are going to get x equals 3, on the other path we are going to get x equals 5. The ideal solution should have been x equals 3, but both MOP and MFP are going to give me the empty set, because I'm going to conservatively assume that both paths may be taken. And so the solution here is going to be empty set for both MFP and MOP. Now, is it true that an MFP solution is always equal to the MOP solution, as in this example? The answer is, let's wait and see. Okay, so here's another example. Y equals square x, y is greater than equal to 0, let's say, and this is, okay, even here I wanted to have greater than equal to 0. So y is greater than equal, if it's true, then you basically take a equals 3, b equals 2. If it's false, then you take a equals 2, b equals 3, and at the end you do z equals a plus b. Now, what's going to happen? So now let's assume that our transfer function for the constant propagation is that option 2 transfer function, where we're going to do some nuanced analysis to identify what is constant and what is not. So in the case of MFP, let's look at this case. On this particular path, I'm going to get a equals 3 and b equals 2. On the false path, I'm going to get a equals 2 and b equals 3, and I'm going to meet them. And the meet here is going to give me a value here, which is 5, the empty set. And this is something that we have seen in our previous modules as well. And so in the MFP, we are going to apply the transfer function of z equals a plus b on phi, and that's also going to give me the answer phi, which is the empty set. So the MFP solution for this particular program for constant propagation with the nuanced transfer function is the empty set at the end of the program. Now let's look at what's the ideal solution. The ideal solution would be able to figure out that square will always be greater than or equal to 0, and so the false path will never be taken, and so only the true path will be taken, and on the true path I will get that a equals 3, b equals 2 and z equals 5. So the only possibilities for all executable paths that can reach this particular point, the end of the program, is a equals 3, b equals 2 and z equals 5. Now let's look at the MOP solution, the meet over path solution. The meet over path solution says, let's look at all the paths that may reach that program point and then compute the transfer functions and then meet over them. So in one case, it's going to be this path here all the way to the end, and here the transfer function is going to say a equals 3, b equals 2 and z equals 5. Alright, so on this path I'm going to get the value a equals 3, b equals 2, z equals 5. Similarly, on the other path, I'm going to get the value a equals 2, b equals 3 and z equals 5. And what is our definition of MOP? Now I meet the two values. So I first compute the transfer functions on the full paths, and then at the very end I meet those values. And so when I meet those values, what am I going to get? A and B are going to get cancelled because they are holding different values, but Z is going to remain. So the meet over path solution here is Z equals 5. And now in this particular example, the MFP is not equal to the MOP solution. And what we actually see is MFP is not equal to MOP and MOP is not equal to ideal. In fact, it's not just not equal to, we can show that MFP is always less than equal to MOP and MOP is always less than equal to ideal, where less than equal to is based on the semi-lattice partial order operator. So in this example, we can for constant propagation, it is easy to see that the empty set is less than equal to the singleton set, which just has z equals 5, which is less than equal to this set which has 3 elements in it, a equals 2, b equals 3 and z equals 5. Why is this true? Because recall that the less than equal to is nothing but the subset operator for the constant propagation algorithm.